For the second problem, the first one is y since stationary process, and this process has two characters. The first one is we know the exact value of this process is constant. Another one is the autocorrelation is a function of a difference, as function of a time difference. So for two variable with the same time difference, it should keep same. So next one is the independent increment process, and the interval and we assume like we did in the Poisson increment process. So actually, Poisson increment process is one of the independent increment process, and the interval t1, t2, and from t3 to t4 are not overlapping, and so the random variable of this random difference of random variable between these two interval are independent, and so Poisson process and random walk are both increment process. And the next one is the Markov process. This process is actually I guess it's one of the most important process in stochastic, because its definition is like the past has no influence on the future when the present is known. So it's like the future. It's like the outcome in the future is at most influenced by present. So it's a simplify the whole process. And for the next one is a normal process. The normal process is xt is normal if the random variable from xt1 to xtn are joint normal for any n and any t1, t2, and etc. tn. In the density function is this gigantic formula here, and we use so xt. This is a vector version, because there's a multiple variable, and for this one is capital X, and use eta to denote the exact value of x, and c is equal to, it's like auto covariance. And for strict sense stationary process, so xt is the strict sense stationary process if the statics not affected by a shift on time axis. So this basically means it cannot affected by time. So the white noise process, if we use VT to denote the white noise process, and WT is a Wiener process. So this is a different. This one is a derivative version of a Wiener process, and we have its exact value is equals to 0, and the autocorrelation is QT1 times the delta T1 minus t2. And for the mean ergodic function, a mean ergodic process is the limit when t goes to infinity, 1 over 2t, and the integral of xt with respect to t from minus t to t. So this one is equals to the mean of xt. And for the last one is martingale process. So this process is condition version of any process. So this one is the mean of xt when we know that when we know that x is for some random time point, we know the random variable xs is equal to x1. So the mean goes back to x1 when s this one the s is the past, some time point from the past.